Let's take a look at the concept of work, and this is kind of a crossover from physics. And let's do the very easy cases first, and then I'll show you why calculus is important to kind of throw into the subject here. So, work back in the day, you might have talked about work in a physical science class, but in an easy case, we can define work as some like applied force times some distance, x. So take a box and pull it across the ground with some applied force. And then the work you do is the force you apply times the distance it's applied. So let's say you apply a 40 Newton force for 10 meters. You would then do 400 joules, introducing you to these units, 400 joules of work. Okay, and again, this is some constant force over a distance, and really this is a displacement because it's a vector. These are vector quantities, and honestly, eventually this work is really a dot product between those things, but let's just stay in one dimension for now. And then we get the work done. Another example, you could talk about the work done by friction. So we could talk maybe about, and don't worry about if you're a little confused where this comes from. I'm just trying to give you examples. Let's take a box and slide it down the ramp, and we can talk about the work done by friction. So the work done by friction would be the force of friction times the ramp distance. We'll call that a distance d. And again, work is some force times some displacement. And the work done by friction is some constant. It's mu mg cosine theta. Again, do not worry unless you're in the physics class where that came from, times then this ramp distance. Again, if I gave you mu, which is the coefficient of friction, which is kind of the relationship between this particular surface, let's just say there's some wooden box sliding down some plastic ramp, that'd be a certain mu. The mass of the box, g, which is the gravitational constant, 9.8 meters per second squared, cosine of the angle times some distance that it slides down the ramp, and that'd be the work done by friction. And really, in this case, the work done by friction is typically almost all converted into heat, and that would be, an energy, and be so many joules. Okay, so why do we need calculus? Well, these are easy examples, and they happen in physics and in engineering where you have some constant force applied over a certain distance. You have this constant friction force applied over a certain distance. But what happens when the force is non-constant? Okay, what if the force changes based on x? And the easiest example of that is springs. Springs are our easiest example, and we would call this Hooke's law. Hooke's law says this, that the force of the spring is negative kx. And let's think about what that says for a spring, or a bungee cord, or a rubber band, or anything kind of elastic here, or anything stretchy. So the force of the spring is negative. What's the negative sign? Well, the negative sign really is the fact that these two things are vectors, and they have directions associated with them. And what that says is, if you take a spring and you hook it to a wall, right, and you stretch it this way, right, you displace it, right, if that's the natural length of the spring, right, nothing's happening, right, it's just that's how long the spring is, and then you make it, and you stretch it to there, x is how far you've displaced it from its equilibrium position. So this distance right here would be x. That's how much you stretched it from its natural length. And if you think about you stretched it to the right, what direction is the force of the spring acting? And again, you pulled it to the right. The spring wants to pull opposite the displacement. So if you displace it to the right, the force of the spring is to the left. So that's what that negative sign is. K is the spring constant. It's the stiffness of the spring. It's in this equation, it's in newtons per meter. And then x is the number of meters. Here's the take-home message, though. The force is not constant. The force is proportional 2x, meaning the further and further you stretch the spring, the bigger and bigger the force gets. And in this case, Hooke's law says it's a linear relationship. Linear meaning, if you look at F versus X, and I'm going to go ahead and get rid of the negative sign, then it's some linear relationship where the slope here is K. Well, if you stretch it 1 meter, there's your force. If you stretch it 2 meters, there's your force. And again, think of stretching a rubber band. Stretch it a little bit. Think about the tension in the rubber band and stretch it more and more and more. Every time you increase X, you increase the force. So this is a non-constant force. And so then the question is, what's the work done? Well, it turns out that the work done is the area under this curve. And again, that's what the calculus says. The work done to stretch that first centimeter is that much, that much, that much, that much. And when you think about it, I really need to accumulate the force over this. And so now we have our real definition for work. Work is the accumulation of F, where F is some function of X, dx. And again, if F is constant, well then, yeah, you can factor it out and then you integrate dx and get X, and all of a sudden you get these two formulas. But if X is non-constant, if the force is somehow related to the displacement, then you have to integrate here. So for the work done by a spring, which is the same thing as the energy stored in the spring, again, the negative sign doesn't do anything other than tell us the direction of the spring force. But if we're finding the work here, we can drop that. If we integrate kx dx, we get 1/2 kx squared, which is the work or the potential energy. And again, I know that's getting a little more physics involved. The potential energy stored in the spring. Again, it's kind of semantics. The work you do is this equal to the potential energy that it now stores. Potential energy is the ability to do, work in the future. Okay? And again, why do we have to do this? Because this is only for constant forces. Now we have a force that's a non-constant force. We've all played with balloons or rubber bands or stretchy things where we can feel that the force changes as the displacement changes. And if we want to find the work done to stretch at a certain distance, and again, this is stretching from some, in this particular case, this is just going from 0 to some x, right? And then you get the energy as 1/2 kx squared. But we could have stretched it from x1 to x2, and then we would have had to do, a definite integral. Springs are probably the most, the classic thing that people introduce to do work. I'm going to do 2 other examples. And again, I did 2 kind of basic examples where we don't need calculus, and the spring is the easiest one. Again, if you think of the area under the curve here, that's x, and that's kx. And so, of course, then the area of a triangle is 1/2 kx squared, 1/2 kx squared. Again, this is the work done to stretch in that little bitty amount, and then calculus says we need to add up all those amounts. All right, so now let's do 2 more, and I like both of these examples. They're kind of fun examples. One is the leaky bucket, okay? We'll call it the leaky bucket problem. Leaky bucket. Okay, so I'm going to throw out a bunch of numbers here. All right, so we got this bucket that's on the ground. Okay, we want to lift it. Okay, we want to lift it 25 meters. Okay, and we know that when it gets to the top, half the water has leaked. Okay, so it's leaking. Okay, it starts out at 40 kilograms of water, and the bucket itself is 10 kilograms. So it's a 10 kilogram bucket. Okay, so a 10 kilogram bucket full of an additional 40 kilograms of water. We want to lift it 25 meters, and we know that half the water has leaked out by the time we get to the top. Okay, so what's the work done? The work done is going to be twofold, and the best part of this problem is it shows both things. The total work done is the work to lift the bucket and the work to lift the water. Again, work you're going to think about is the accumulation of a force over distance, and we got to lift this. Okay, so The work done to lift the bucket, well, that's actually really easy. The work to lift the bucket. And again, we have to go over a little physics. This is the mass of the bucket, and the weight of a bucket, the force of gravity, is mg. So we got to multiply by g. Okay, so g is 9.8. So then the mass of the bucket is 10, which means the weight of the bucket is 98. 98 newtons is the weight of the bucket. Well, that's actually really easy. Then the work done to lift the bucket is just the force of the bucket, 98, times 25. Right? This is just the force times the displacement. That's easy. That's the work to do the bucket. Now, what about the work to do the water? Well, the water is going to leak out. It's a non-constant force. Let's think of this water weight. So what does the water happen? Okay, so the water is 40 kilograms of water. So then the total weight of the water, water weight, right, which is force, right? Weight is just the force of gravity, is going to be 40 times 9.8 is the total, but what's going to happen? What's going to happen is we're going to lose so many newtons per meter. And again, what did we lose? Well, if we lost half of this, we lost 20 kilograms. So we're losing 20 kilograms, which is 20 times 9.8. That's how many newtons we lose per meter, 25 meters. All right, you got to think about that for a second. Think about all those numbers. We need a formula for the weight of the water as a function of x. This is the total weight of the water at the bottom, but we're going to lose 20 kilograms. Remember, half the water is leaked, so we lose half of this. 20 kilograms, which is really 20 times 9.8, which is how many newtons of water we lose per meter. In 25 meters of lifting, this is how much we lose. So if we lose this amount per meter, then this is an equation for the weight of the water as a function of x. And again, we need all these values. So let's take 40 times 9.8, and that's 392. 392 newtons minus, and if we take 20 times 9.8 divided by 25, we're losing 7.84 newtons per meter. Again, this is the force of gravity, the water's weight as a function of x. And again, you have to be able to figure out f of x. If you figure out f of x, then you're good, because what are we going to do after that? Well, we're going to accumulate. We're going to go from 0. We're going to lift that thing to 25. And our force is right here. 392 minus 7.84x. And we're going to lift that force over the distance dx. Right? This force, we're going to lift it and lift it and lift it and lift it. And every meter, every dx up, our force changes. At the beginning, when x is 0, the force is 392, meaning all of the water. When we get all the way to the top, when x is 20, so if we just let x be 20, 392 minus 7.84 times, 25 I mean, then we get 196. Well, of course, we get 196 because we only weigh half as much, because that was the given information. Okay, so let's kind of work out all these numbers then. So 98 times 25, that's 2450, 2,450 joules. And then if we do math, this is an easy integral, but we can also just use math 9 if we wanted to. Comma x, comma 0, comma 25, and we get 7350 joules. That's how much work it is to lift the water. And let's add that to the 2450, and all of a sudden we get 9,800 joules of work to lift that water. Again, the leaky bucket problem is a nice example because it has the work to do. The bucket is really easy. It's just the weight of the bucket times the distance you're going to lift it. Right? It's like an mg and an h. If you're in a physics class, this is just mgh. which is potential energy, which is the same thing as the work done to lift something up to a certain height. And then the bucket's water weight, well, it leaks, so it's some function of x. Okay, makes sense? All right, we'll do one more problem, which is really similar. We're going to lift. We are going to lift something. This is kind of a rope problem. And the rope problem is very similar. So you have something there, and you're going to lift this rope up. Right? Maybe there's a pulley there or something. You're up here, and you're up here doing all that work. Okay, so let's give you some stats here. The rope itself has a weight, right? It's not in physics we always say the rope is a negligible amount. Well, no more. We can do this. So the rope weighs 0.5 newtons per meter. That's the weight of the rope per meter. The length of the rope is 40 meters, right? So then that tells you that the rope is really 20 newtons in terms of its weight. Okay, the box that you're doing, the actual box, let's make that 10 kilograms. And again, 10 kilograms is 98 newtons in terms of its weight. And again, weight is just the force of gravity. Okay, so you got to think about what happens here. When you pull this up, what do you have to do? Well, you have to do work to do the box, right? But that's easy because that's a constant. The box's weight isn't changing. It's just 98. Oh, and that's, what do we, oh, we're pulling it up 40 meters because that's the length of the rope. Okay, so that's a good one. So then we have the box, which is 98 times 40. Again, 98 times 40 is 39.20 joules. Okay, that's the work to do the box. But now we need to do the rope. And again, you only have to pull, if you think about like that part of the rope, you don't have to pull it up 40 meters. You only got to pull it up that much. And over here, you only have to pull that up that much. Or you can think of the fact that you're pulling the rope all the way up, but the force of the rope is changing because the weight of the rope is changing, because once you've pulled up some of the rope, there's less rope to pull up and it doesn't weigh as much. So you can think about the work done, again, is going to be this accumulation of the force over the distance. Each time you pull the rope up a meter, there's less rope to pull. So the force of the rope, the weight of the rope, changes. Okay, so we need to get an equation for that. We know we're going to integrate from 0 to 40. And then what's the equation? Again, what is an equation for the force as some function of x? Well, think about the rope starts out at being 20 newtons. And then every time you pull 1 meter, it weighs what? It weighs 0.5 newtons less. Think about that for a second. This is the rate, this is the weight per meter of the rope, and every meter you pull up of rope, it weighs this much less, because that's the weight density of the rope. Think about when x is 0, the force is 20, meaning when x is 0, you haven't pulled anything up yet, you're holding the entire weight of the rope, 20 newtons. When x is 40, then the force is 0, because once you've pulled 40 meters worth, there's no more rope to pull because it's all gone. So this equation should make sense. So over here, 20 minus 0.5x dx. Okay, and just type that out real quick. Math 9, 20 minus 0.5x, comma 0, comma x, comma 40, and we get 400 joules of work is required, and then we can add that to the 39.20, and we can get a total work done of 43.20. And again, all of these questions go back to the same thing. If your force is some function of x, force changes, and you have to integrate it over that distance. In this case, every time you pull up the rope, you get that little section of rope out of there, and then you don't have to pull it anymore. So the rest of the rope only weighs, 19.5 newtons. Then you pull the next meter, and then the rope only weighs 19 newtons. So this force changes, and so you have to integrate that accumulation of the force over each one of those distances from 0 to 40, and then you get the total work done, which is in joules. Okay? If you happen to be in other stupid units like feet and pounds and inches, it's stupid. Any real science is going to be in meters, kilograms, thus newtons, and then joules. So if your calculus book doesn't do that, then you just have to work with those units as given. But just know that when you get to a real physics book or an engineering class, you're going to be in these units. Okay?